Hello students. So today I am going to explain theorem 2, coming to the statement that V of f is a vector space and W is non-empty subset of V. So then prove that the necessary and sufficient condition. Once again, if and only if theorem. So for W is subspace of V is A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. So here we have to prove if and only if statement. So the first statement is W is subspace of V. And the second statement is A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. So we have to suppose the first condition and we have to prove the second condition. So while in converse part, we have to suppose the second condition, and with the help of second condition, we have to prove the first condition. So this is what we have to prove in this theorem. Okay. So coming to the proof, the common hypothesis was V of f is a vector space and W is subset of V. So that I am writing given V of f is a vector space and W is subset of V. This is also given. Okay. So now I am supposing that first suppose that W is subspace of V. I am supposing that W is subspace of V. So according to the definition of subspace, if you want to say a non-empty set to be a subspace of vector space V of f, first of all, it should be a subset, and after that, it should be a vector space. Okay, it means whenever you are saying that W is subspace of V, then W itself is a vector space. Okay, that is by the definition of subspace. So I can write this implies W is a vector space. Okay, so it means we are having all the conditions of vector space definition holds in W. Okay, right. So now we have to prove the condition, that is, so we have to consider two elements. Let A comma B from F and alpha comma beta from W. Okay, so we have to consider these elements and we have to prove that A alpha plus B beta belongs to W. Okay, so since A belongs to F comma alpha belongs to W, by closed scalar multiplication property or by simply closed scalar multiplication, we have A alpha belongs to W. Yes, by the definition of vector space, second condition. The first condition is abelian group condition. Coming to the second condition, that is closed scalar multiplication property. So whenever we are having an element from the scalar field and from the vector space set, the product of those two elements should also belongs to the vector space set. Okay, so here A belongs to F, that is a scalar field set, and alpha belongs to W, that is our vector space. So now the product of those two elements should also belongs to W. So this is by the definition of vector space. We are writing A alpha belongs to W with the help of vector space definition. Okay, so once again, I am writing also comma since. So B also belongs to F and beta also belongs to W. Once again, by the same property, by closed scalar multiplication, we have B beta belongs to W. Okay, so this was also by the same property in vector space definition. So whenever we are having an element from scalar field set and vector space set, so the product of those two elements should also belongs to the vector space set. So now we are having two elements in W. Okay, now we are having two elements in W. One is A alpha and the second one is B beta. So once again I am writing now A alpha comma B beta belongs to W. Then by closure property, now I am using closure property. So since W is a vector space, the first condition in vector space definition is abelian group. In abelian group, we are having 5 conditions. The first one is closure property. Yes, you can use closure property. So what is closure property? If you are having any two elements in that particular set, then the sum of those two elements should also belong to the same set. That is closure property. So that by closure property, we get here, since the operation is plus, so that we can use plus. Okay, we get A alpha plus B beta belongs to W. So this is because of closure property in W. Closure property in W, since W is a vector space, implies W comma plus is an abelian group, implies closure property holds with respect to addition. So closure property is nothing but whenever we are having two elements, then the sum of those two elements should also belong to the same set. Okay, so with the help of vector space definition, I have proved the condition. That is the second part. Okay, so after that, we have to suppose the condition what we have proved now, and you have to prove that W is a subspace of V, converse part. Okay, so now I am supposing that. Now suppose that A comma B belongs to F and alpha comma beta belongs to W, implies A alpha plus B beta belongs to W. So this is what we have proved in the above part. So now we have to suppose this part, and now we have to prove that W is subspace of V. Once again, according to the definition of subspace, in order to prove W is a subspace, first of all, W is subset of V. Yes, it is clear. So clearly, it was given in the hypothesis W is subset of V. After that, we have to prove that W itself is a vector space. W itself is a vector space. So since W is subset of V and W itself is a vector space, by combining the two statements, then we get W is subspace of V. So it means now we have to satisfy all the conditions of vector space definition for W. Okay, right. So first one, I am going to prove the first property. The first one is abelian group property. In abelian group, once again, we are having 5 conditions. So that first condition is closure property. Closure property. So in closure property, we have to consider 2 elements. So I am considering let 1 comma 1 belongs to F, and yes, in scalar field, yes, definitely 1 belongs to F. I am writing 1 2 times. 1 comma 1 belongs to F and alpha comma beta belongs to W. So this implies by our converse supposition. So what is our converse supposition? Whenever we are having 2 elements in F and 2 elements in W, we can write A alpha plus B beta belongs to W. So that I am writing 1 into alpha plus 1 into beta belongs to W. So this condition we can use now. So this implies we get alpha plus beta belongs to W. So this is closure property. So if I consider 2 elements in W and I have proved that sum of those 2 elements also belongs to W. So therefore closure property holds. So therefore closure property, and this is true for all any 2 elements in W. So therefore closure property holds. After that, I am going to prove the identity property, existence of identity. Existence of identity. Now I am considering 0, 0 from F. In scalar field is nothing but all scalars belongs to the set F. So I am writing 0, 0. And alpha, beta belongs to F. Belongs to W. In vector space, in W, you have to consider vectors from W. Once again, you have to use our converse supposition condition, that is A into alpha, that is 0 into alpha plus 0 into beta belongs to W. So this implies we get 0 into alpha is 0 plus 0 into beta is 0, so that we get 0 belongs to W. So this is identity property. So in identity property, what we have to do is we have to say that 0 belongs to that particular set. Yes, I have said that 0 belongs to W. So therefore the identity element is 0. Okay. Next, coming to the next property, that is inverse property, existence of inverse. Once again, you have to consider two elements in F. One is -1 and the second one is 0. Since F is a field, so I have already discussed about the definition of field in our first video. Okay, so field is nothing but, first of all, it should be an abelian group. After that, it should be a semi group. So abelian group with respect to addition means it should satisfy identity property, inverse property, all these conditions. So identity property is nothing but 0 belongs to F. So that I have used 0 two times in second condition, that is identity property condition. Similarly, -1. So whenever 1 belongs to F, then the additive inverse of 1 is -1 should also belongs to F. Otherwise, inverse property does not hold in F. Then F is not a field. So, but you are saying that F is a field, so that inverse property clearly holds in F. So that I am writing -1 belongs to F. Okay, and also 0 belongs to F. And once again, I considering alpha, beta in W. This implies, once again, by our converse supposition, we can write -1 into alpha plus 0 into beta belongs to W. So this implies -1 into alpha is minus alpha plus 0 belongs to W. So this implies minus alpha belongs to W. So this is inverse property. I consider alpha, here you have to write the same element itself, same element two times, so that 0 into alpha. So 0, so minus alpha belongs to W. So I consider alpha in W, so that I get minus alpha belongs to W. So in place of beta, alpha, if you consider beta, then also we get minus beta belongs to W. Okay, or any other element gamma, so then also we get minus gamma belongs to W. So this is inverse property. Okay, we have to consider only one element there, not two elements. So I am writing, therefore inverse property holds. So like as yesterday, in yesterday's theorem also we have proved all the three conditions, but in different order. Now we have proved all the properties in the same order. After that, we need not to prove closure property, associative property and commutative property, because I am writing the reason. Since W is subset of V, so all the elements in W are the elements in V. So if you want to prove associative property, I have to consider three elements in W. Since W is subset of V, then those three elements belongs to V. Since V is a vector space, then clearly associative property holds. Like as associative property, commutative property also holds. So therefore we say that W comma, therefore the vector addition is associative and commutative. It means I am saying that both associative and commutative property holds under addition in W. Okay, is commutative in W. Therefore, we can write W comma plus is an abelian group. So in order to prove W is a vector space, first of all, we have to prove that W comma plus is an abelian group. So it was clear. So after that, we have to prove the closed scalar multiplication property. So for that, I am considering A comma 0 belongs to F and alpha comma beta belongs to W. Every time we have to keep it in mind that the condition what we have supposed in our converse part. That is A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. So every time we have to use that particular condition to prove the conditions. So in vector space second definition, in second condition of vector space definition, we have to prove that A alpha belongs to W. For that, I am considering A comma 0 in F and alpha comma beta in W. So once again, by our supposition, we can write A into alpha plus 0 into beta belongs to W. So this implies A into alpha is A alpha, whereas 0 into beta is 0, so that we get A alpha belongs to W. So this is the closed scalar multiplication property. So therefore, closed scalar multiplication property holds. Okay. So after that, we have to prove the postulates. So once again, I am saying that since W is subset of V, so other postulates of vector space holds in W. So we need not to prove the postulates. So we can write directly that those postulates also holds in W. Okay. So whenever you say that W comma plus is an abelian group, closed scalar multiplication property holds, and also the postulates holds in W. So therefore, I am writing that the W over F is a vector space. Is a vector space. So already it was given that W is subset of V, and now we have proved that W is vector space. By combining these two statements, therefore we can write W of F is subspace of V of F, or simply you can write W is subspace of V. Okay, hence the theorem. Okay, so this was also an if and only if theorem. So in the first part, I have supposed that W is subspace of V, and I have proved the condition A comma B belongs to F and alpha comma beta belongs to W implies A alpha plus B beta belongs to W. In the first part, I have proved that condition, and in the second part, I have supposed that condition and I have proved that W is subspace of V. Once again, if you want to prove W is subspace, first of all, it should be a subset. That was already given. After that, we have to prove that W is itself is a vector space. It means we have to satisfy all the conditions of vector space definition. But in the proof, I have proved only closure property, identity property, and inverse property. So remaining all properties, and of course, closed scalar multiplication property. I have proved only 4 properties. So whereas all the remaining properties holds in W because W is subset of V. It means whenever you consider any element in W, clearly that particular element belongs to V, so that the remaining conditions holds in W. So we need not to prove all the conditions of vector space definition. Okay, so therefore W is a vector space and hence W is subspace of V. This is very important thing. Okay, thank you.